Center for Autonomous System. Okay, let's welcome Maani. Ghaffari gave us a talk. Maani graduated from UTS Center for Autonomous System a while ago and has been working mainly in US. So yeah, let Maani talk right now. Okay.
Thanks for having me. It's great to come back and see all of you and talk about what I've been doing. It's been a while, it's been 5 years. So what I'm going to talk about, I try to put it in a common context, but it's some of basically work I've done since I left CAS and came to Michigan. So some context for what I started working and formed a research lab around this topic. My field is robotics and autonomous systems, just like all of you in CAS. But in particular, the question that I had to answer to separate from computer vision, machine learning, all the tools that we use was that what is the unique aspects that robotics bring in to science and engineering besides common goals that we have, like serving society, improving quality of life, dignified life, and fulfilling one's potential. And that's embodied intelligent aspects of robotics. That brings a lot of capabilities to an autonomous system because the robots can move and accomplish some tasks. We can replace humans, we can do exploration, we can collaborate with humans. These are unique to the field of robotics. Now I'm going to focus on a particular platform, legged robots, because that's something I've been working on recently. But the context, of course, is applicable to other platforms as well. Now, why legged robots are good? Because they can traverse discrete terrains that are not traversable by wheels. And that we have a lot of lands that maybe 60 to 70% of lands on our planet are not traversable by wheels. Besides that, legged robots can operate in environments that are made for humans. Indoor environments, stairs, structured environments are very suitable because they are made for us, and legged robots can operate in those environments too. So there are a lot of opportunities in these basically areas for robots and in particular autonomous systems. We can navigate and traverse the disaster side, delivery and transportations are very focused topics in the US now. There are a lot of companies working on delivery and transportation. Collaborating with humans, which is an emerging field of human-robot interaction. I know it's old, but recently more and more people are working on it, and it's a focused topic. And pandemic response, we learned that when something like pandemic happens, it's nice to have robots to move around and help with delivery of goods, medicine, and dealing with basically complicated situations in cities. One particular problem is the state estimation. The problem is that the robot is moving. There's a frame attached to the robot. We have a word frame. We want to know where the robot is located at any time. Now we call this localization if we want to track the global trajectory of the robot. But if we just want to track at a very high frequency, typically we call that a state estimation, and we might use something like Kalman filtering for that task. This observer operates at high frequency, something like 1000 Hertz or 2000 Hertz, because it needs to provide velocity feedback and orientation feedback to the controller. Whereas a SLAM or localization, they can operate at a lower frequency. So we want to estimate this pose and velocity and possibly calibration parameters. So we could think about it as a state matrix of rotation, velocity, and position. Now, what is the problem? The problem is a lot of times when robots rely on vision and perceptual data, they might fail. For example, you can see that when there's a fire, which you experienced it in Sydney, in California here. We experience fire every year. When the robot is perceiving the environment using camera, of course, it's foggy, it's not clear. Using LiDAR, you see the picture in the bottom. We get a lot of outliers and artifacts. So vision doesn't really work well for the robot, besides their low frequency. The low frequency signals with high bandwidth. It's very difficult to process an image or LiDAR point clouds at a high frequency. On the other hand, proprioceptive methods use joint encoders, IMU, and contact sensors. They can operate at a very high frequency, 1 to 2 kilohertz. So unless the hardware fails, we can always use proprioceptive state estimators for tracking, and that's very attractive. We did an experiment on a legged robot. This is, I believe, is done using a factor graph. We combine vision, contact, and IMU data. When we drop vision, the uncertainty grows immediately around this gray area in the middle, runtime 20 seconds that you can see. Whereas if we use contact, the uncertainty does not grow, and we can still track reliably. And that's very important. When we lose one modality, we can still operate reliably. That robustness is very important to today's robotic systems. So this motivates us to build a state estimator for legged robots such that we rely on proprioceptive signals at its minimal state. This is not meant to replace localization or SLAM. This is a high frequency state estimator that runs on board, is very low cost, and provides odometry. That odometry can be used to initialize a lot of perception algorithms and SLAM methods. So it has a complementary role. So for a legged robot, we have joint encoders. We can use the kinematics to know the foot position relative to the body frame of the robot. We have contact sensors as well. When the robot walks on the ground, we know when we're touching the ground. This combining IMU and leg data from kinematics is known as leg odometry. And this is a problem in legged robots. Typically, we use an EKF to extended Kalman filter to fuse data and estimate the robot pose, velocity, and IMU biases. Now, you are familiar well with Kalman filtering in CAS. If the system is linear, the filter is basically the optimal filter, and that's not a problem. If the model is nonlinear, we have to linearize. If you linearize directly around the operating point, that will give us the extended Kalman filter. Later, we learn to do better than that. If we linearize the error dynamics, that will basically pushes the linearization around the identity, around the true state, and the error will be around basically the zero. And that tends to be working better in practice. However, still, it does not exploit any particular geometry from the problem. So bad estimates can lead to incorrect linearization, and that leads to poor performance, and that creates a positive feedback loop. And probably this is the reason now we are not very excited to use Kalman filtering for SLAM and solving localization problems. Now, when I was a student at CAS and was finishing my PhD DSOP and shooting, I think you were working on invariant Kalman filtering with Jackson and Kanji, and I knew a little bit about it, but later I learned more about this invariant Kalman filtering, and it was very interesting to see that how it fits into solving this problem. So just a quick overview of invariant Kalman filtering. This is a geometric filter. We see the state as a Lie group instead of Euclidean space because we're dealing with rotation. A matrix group called SO3. If you include position, that will be SE3. Now, if we want to find a class of functions that will lead to log linear error dynamics, after some algebraic manipulation, we will end up with this group affine property. So this magic formula that shows here comes from the fact that we search for log linear error dynamics. Then we find out that if a function, a process model satisfies this property, then the error will be basically log linear. And these are matrices, so we do matrix multiplication when we write it next to each other. So that was a very interesting observation by Barou and Bonnebel from France. So a correct definition of the error in this framework will be state as a matrix multiplied by the inverse of the true variable. If we do it from right, that will give us the right invariant error. If we multiply the true state's inverse from left, that will give us the left invariant error. And the name comes from the fact that if we shift both terms from left or from right, the shift will disappear, and that means that the error is invariant to the group translation. This simply means that the error propagation is independent of where the robot is operating in the physical world, and that intuitively makes sense because the relative movement should be important, not the absolute coordinates for a physical system. The world coordinates that we choose to track the system, it's an imaginary concept. For the robot, the relative motion should lead to accumulation of the error, not the particular choice of coordinates. So these exponential coordinates and matrix groups respects this structure nicely, and we get log linear error dynamics. Now, if we want to solve this contact-aided invariant problem, we have an IMU, we have contact sensors, and we have joint encoders data. What we want to do, we want to estimate base, pose, and velocity. And we also track the contact points in the filter as well. These are the robot foot frames that you see. So one interesting similarities here that might surprise you is that this problem is very similar to landmark-based SLAM. You can think about the base frame of the robot here to be the robot, and each foot position is basically a landmark. But the only difference is that the landmarks, when the contact is broken, will disappear and we will never observe them again. But however, in SLAM, we of course re-observe the landmarks for loop closure. So for a moment, we observe a landmark, we can include it in the filter, and then when the contact is broken, we marginalize it forever. Now, for the propagation, we use IMU and contact. So the contact helps us to remove the drift. For the correction, we use kinematics. So the correction is relative. We only say that the relative position of the foot with respect to the IMU frame is what we read from the forward kinematics function of the robot. And that will help us to correct the propagation step in the filter. Now, if you derive the filter, this will be a common filter on Lie group. What happens, a surprising result is that the linearizations are constant. We get A and H matrix. These are process model, basically linearization matrix, and H is the measurement model linearization matrix. These are constant. That means the propagation of the error and in the correction step, we are independent of the state estimate. No matter how far is the trajectory that we're tracking from the true state, we can always converge in under certain nominal regularities. In particular, for a deterministic system, this will converge. When we add noise, the theoretical results are lost, but it works very well in practice. So this solves a long-standing problem that linearizations are basically leading to divergence because they are constant. There is no danger of that. And then the correction step, it looks a little different because we have Lie groups. We have to calculate innovations in the tangent space, and we take the exponential map for update. But in general, it looks very similar to a regular Kalman filter. Now, to give you an idea of what we gain by using this formulation is that the error is log linear. If you compare this filter with a quaternion-based extended Kalman filter, which is the red point cloud you see using a basically covariance propagation and sampling to visualize it, the quaternion EKF treat the space basically to be decoupled. It just tracks a rotation separately and translation separately and leads to flat covariances. However, the right invariant EKF that we implement can track a nonlinear covariance, a curved covariance. This covariance is linear in the tangent space, but when we take the exponential map, it becomes nonlinear. That matches the true covariance. Now, why this happens? There's a simple reason. And the reason is that first rotating and then translating is not the same thing as translating first and then rotating. This is a very simple and overlooked basically fact here. In the quaternion EKF, the quaternion part, of course, is correct. That's rotation formulation is equivalent of SO3. There's no difference in the sense of correctness. But the problem is that quaternions are considered to be a separate part of the state, and then the translation error is not coupled with the rotation. But when we think about the state as a matrix, and then we calculate the error using matrix multiplication and inverse, what happens is that the rotation error and the translation errors are coupled. And this is mathematically because the SE3 is a semi-direct product of SO3 and R3, not the direct product. But the simple reason is that the order of rotation and translation are important, and that should be reflected in the definition of the error. So when the rotation is small, they have similar performance. But in general, invariant EKF is not sensitive to this problem, and it's a better choice. Now, things that we can do. We run this filter on a bipedal robot on campus here in Michigan. The filter is running on board at 2 kilohertz. We get LiDAR point clouds basically at 10 hertz. Every point cloud has 10 packets. We need to compensate the motion of the spinning LiDAR as the robot moves. So what we're doing, we read the pose estimates from the invariant EKF. We compensate the motion of the spinning LiDAR, and then accumulating the LiDAR point clouds using this invariant EKF for 10 seconds. If we do it for a long time, it will drift, but for a window of time, it's accurate enough that we can reconstruct the scene by just visualizing the point cloud from the LiDAR. This is not a map. This is just directly visualizing the point cloud that we read from the LiDAR. That is descriptive enough that we can see the scene as the robot is moving. I think the color map here is the intensity we read from the LiDAR. And you can see from the image in the bottom right that the robot is walking and shaking a lot. The sensor is shaking, but the point cloud we see is very stable. So what we get in practice is worth the effort of going through that basically math and driving a filter that respects the geometry of the space that we are solving the estimation problem. By the way, if you have questions, you can feel free to interrupt. If I'm going too fast, you can pause me and just ask your questions.
Yeah, I think it's all good. Yeah.
Okay, so Okay. So we'll continue.
Maani, just one quick question. The context that you're talking about is just a discrete measurement, contact or no contact?
Yes, that's a good question. The contact is not a typical measurement we're used to it. It's a binary measurement. We just know that the foot is in contact with the ground or not. It's like a classification of the state of contact, no contact. So it's binary. But how we get it in practice for the bipedal robot, there's a spring, and then there's a simple function that looks into the deflection of the spring, and then based on the force, it will threshold it to contact, no contact. But ultimately, for the filter, is binary. That's right.
And that means that as soon as you touch, you basically have got a positive binary. Basically, as soon as because I've seen the feet, obviously it's got a operation. It rotates. As soon as it touches, you just have a positive, basically.
Ideally, because exactly that motivates what I'm going to talk about, plus not having that sensor. So ideally, as soon as we touch the ground, we know the robot is in contact. And as soon as we lift the foot, we know there is no contact. Because not being able to do that, it will lead to false, basically positives and false negatives. And that's not good for the filter and for the controller. But ideally, that's right. We want to know it as soon as possible.
Thanks.
Hi, Maani. Very quick question. So as you mentioned about using the feet location as the features, did you can see the ground is flat, then all the features are on the same plane?
If the ground is flat, all the features. So we don't track any features. Maybe I didn't understand the question.
Oh, you mentioned you mentioned to use the feet locations as landmarks, right?
Mm-hmm.
From the encoder. Yeah. And in this case, did you can see all the landmarks are on the same plane? Because
so to clarify, I made an analogy between foot positions and landmarks, but we do not use vision. There is no vision in this work. So all the trajectories just coming from an IMU, contact data, and joint encoders.
Oh yeah. What I mean is all the landmarks are considered as on the same plane.
On the same plane? No, they are not, because forward kinematics will tell us the basically a good estimate of foot position relative to the body frame, IMU, the torso of the robot. And that depending on what height the robot is walking, that can change.
Okay, then will it provide information about like getting a better localization result of the robot frame?
Can you repeat the question, please?
Okay, so I'm thinking if you consider it as landmarks and you only observe them once, they will not get any information for the localization, right?
That's right. So if we do observability analysis that we've done in the paper, the position is not observable here. We can only track. The yaw angle is also not observable unless we use a magnetometer. So the observable states are roll, pitch, and the velocity of the robot.
Yeah, sure. Thanks, Maani.
Yeah.
Adi, what kind of error growth you have? What kind of percentage? Like 0.5% or roughly, compared to wheel odometry, if it's a wheel vehicle, maybe 1% is something you think you can get, right? I mean, with the robot, it's a lot harder, obviously. It's much harder to.
So I don't have a lab tested percentage, but the height drift is severe, which motivates this learning based combination. If we go, let's say 200 meters around the field that we did it, we might get 1 or 2 meters height drift. But the top view, the drift is maybe much less. It's less than a meter, less than half a meter. So it's the top view, the XY location is really good, but the height drift can be severe.
Okay, all right, thanks, Maadi.
Yeah, there's actually sorry, Maani, there's actually a question from Lihan, and I know the answer, but I'll let you do it.
Yeah, you want to?
I think the question is whether it's a 2-leg robot or 4-leg robot.
Because I know it's the Michigan one, the 2-leg.
Oh, so the previous result was using 2 legs.
Okay.
With bipedal. Now this work is on quadruped, 4 legs.
Okay.
Since I become independent, I abandoned that bipedal robot. So this is a lone robot from MIT Sangbei Kin's lab.
Okay.
I'm working on this robot now. So now one big problem is when we, I have a picture of the robot, I think somewhere here. Yeah. So this robot does not have contact sensor because it's lightweight. There is no spring attached to the leg, or there's no dedicated contact sensor. So that filter is nice and works well, but without contact, we go back to the same problem that if we integrate IMU, even if we do it correctly, it will drift. So on top of that, some basically robots during operation can break the contact sensors or they can degrade. That's the problem, which causes that height drift that I just mentioned. Now, the natural idea is that a natural question is, to ask is that how can we make the robot aware of the environment? Because just using model, we're just moving with assumptions. And to use data and making the robot aware of the environment and interaction, a natural tool to use is deep learning at this point. So what we want to do, we want to estimate the contact events using a convolutional neural network, which is a simple classifier in this case. It's a very lightweight network. We can run it in real time. And runs a classifier that will tell us at any time step, if a leg is in contact with the ground or not. The inputs are the IMU data, accelerometer, angular velocity, joint encoders, and joint position and velocity, but also foot position and velocity from the kinematics. Foot position and velocity are somewhat redundant because the network could figure out possibly forward kinematics, but we're simplifying the network's job by giving it as the input. So what we want to do, we want to estimate contact and then give it to the same filter and hopefully solve the problem. So to do that, we collected data on 8 different ground types on campus: asphalt, concrete, forest, grass, pebbles, rock, road, sidewalk. They're very different with different type of interaction with legs. Not so slippery. Of course, in winter in Michigan, we have a lot of snow. We are planning to maybe collect more data. But because we're collecting proprioceptive signals, we can collect a lot of data points. 1 million data points easily by just running robot around for a day around the campus. Now, the ground truth is a problem, but if we move the robot fairly stably, if the view is not blocked, we can run a slam and get the trajectory. We have outdoor motion capture for the grass ground that we can get trajectory as well. So together we can train the network to estimate the contact. By the way, the network is also self-supervised because it will be very painful to label it manually. So we have an algorithm that can label the contact data in a self-supervised way. However, because that algorithm will use future data and past data to look at the window and decide whether this is a contact data or it's an outlier or just a quick bounce with the ground, we cannot run that algorithm online. So we can process data offline to generate data and then train the network to bypass the need for future data. So the learning will bypass the need for future information during online deployment. That's the message here. And then when we combine it, there are cases that the video I will show. Orbislam works well. When it works, it's great. We can run it on the robot. However, it fails when the vision sensor is blocked, whereas the proprioceptive sensor can track regardless of that. So we're running everything at 500 Hertz on the robot, including the neural network after some optimization. Just leave you with this video. and I'll just be quiet.
Maani, can I just ask, are you expecting there to be audio being sent from the video? Because there is nothing, so we just can read, but not hear anything.
Oh, the audio, I just muted it. It wasn't mute. But I think it's okay if you can't hear it.
It's not being sent. It's not being sent through anyway.
The video or the audio?
The audio.
Oh, I think that's okay.
Okay.
It's just the sound of the robot's legs hitting the ground. You're not missing much.
Okay. I have to read though.
So that was when the orbit slam failed. Now, of course, vision is a very powerful sensor, but when it's blocked, there's no way to basically use it. If it's dark, if it's completely dark, for example, we also lose tracking. The perception will fail. This is analogous to we close our eyes, we walk for a while, we can still track, and we want that ability for our robots too. And that's what basically we're doing here. So this is the part I skipped to this part.
So Maadi, the contact constraint is zero velocity at the tip, or is there a slip? Is there a possibility of slip there?
It is zero velocity constraint. So the contact is in the prediction step, the contact enforces a zero velocity on the foot position. That's why we need to include the foot position in the state.
So on that gravel, that may not be, it is at least satisfied at some point, right? Is that what you say? And that's
yeah. So we place a Gaussian noise. It accounts for some slippage, but that's an open problem. If we go on a slippery ground, to what extent we can relax that assumption? The learning will help us to work on this framework, but we haven't done that yet.
Yeah. So the learning can try and at least identify whether there is a zero velocity spot. Okay.
So my personal idea is that if I have an accelerometer on the foot, I can solve that. Or if I can estimate the acceleration of the foot, I can solve that. But we don't have that sensor. So maybe we should create a virtual network of sensors using learning. Because the hardware
you have the orientation to worry about, the leg orientation. So accelerometer may not tell you that precisely. Maybe something else. Yeah, look, it's good. Great.
Future work.
Yeah, it's good.
Okay, so yeah, that assumption is very simple. Zero velocity, basically the foot, when it's in contact with the ground, does not move in the world frame. That's a very simple assumption we make that helps a lot to remove the drift from IMU. It works well in practice, but I think there's a lot more to do in this area. So the code is open source online, the data set is online. Let me know, feel free to contact us if you want to use the data for any project. So what this framework enables beyond just estimating contact is that we know already on what ground type we collected data. So we can easily generate labels for supervised terrain classification. Based on the interaction data and IMU signal, we can estimate the ground type. On top of that, estimating acceleration and friction is very important. Friction estimation is difficult. A lot of sponsors want to have that, and that's a problem we're working on. That extends to wheeled platform as well, because for self-driving cars driving on highway somewhere like Michigan when it's winter, it's a very difficult challenge for something like MPC to operate, because if we don't know the friction of the ground, all the constraints will be violated. Some preliminary results, this is not published work, just to show you that it works. If we just run some tests with some 80, 90%, maybe 60% sometimes accuracy, we can tell what type of ground we're walking on, basically by just touching and hitting the ground. There's a lot of information by just interacting with the environment, and we can learn this type of nature of that environment or ground from contact data and IMU signals.
It's funny actually, Maani, because I've noticed that in asphalt, that's where you have relatively low, well, it's lower, but anyway, 60%. Whereas asphalt, I would imagine that that's where the constraint is held really much stronger and the vision probably is very clear.
That's the part we didn't understand, because the accuracy actually on test data is more than validation data. That surprised us. So we're not publishing anything until we do more tests and understand it. But on concrete is really high. As you said, I thought probably asphalt will be similar, but it's not. Maybe grass is lower. We could assume it's soft or rock road, but it is not consistent, as you said. So that's the end part of basically this area. I don't know if I have more time. I can talk on more topics, but maybe see if you have questions.
Looks like a bit of an unbalanced data set because you have lots of stuff predicted as concrete. Not sure.
It is. It's probably, I mean, we balanced it in the loss function, but this is just a simple test, and
yeah,
it's not super reliable, but this is promising because it is doing something, right? It is. The network can tell us the ground type.
So just a short question. You don't have torque on your motors, right? Because that could solve the problem as well.
We don't have what?
Torque. Like
torque. No. Yes, that's very, very good point. So one problem is that not every robot provides torque or current from the actuators. If we have that, that's a lot of information, and that's very actually useful to estimate contact as well. But
yeah, makes sense.
Two reasons I didn't show you the results, but if you use model-based, you can use dynamics of the robot and model to estimate context, and that's what people do. One problem with that is that the model has some parameters that are inaccurate, like the inertia matrix. The second problem is that for lightweight robots like this mini cheetah, because the legs are so much lighter relative to the body, the model is inaccurate. It doesn't work well. So altogether, it's very painful. It's so much better to learn from data and bypass that part for contact estimation. Besides, this framework will enable us to estimate more quantities using multitasking. And
just a last question. When you're estimating, so there's a bit of noise in the background, but when you're estimating contacts on steps, so like if you bring it on stairs, like does it behave well or not really?
If we estimate contact,
like on a very uneven terrain where like you're going up like stairs, for example, because I guess it's like a bit harder to train for things like that.
Oh, for stairs.
Yeah.
Oh, that stair climbing is a challenge itself. Some PhD students here in Michigan are working to make a controller that a robot can walk the stairs. The robots cannot, especially bipedal robots, cannot climb the stairs reliably. That's the problem. Quadruped robots are more stable, so it's a little like cheating because it's not the controller that is making the robot climb the stairs. It's just the robot is stable already. So if the dynamic can become unstable, that's a very difficult problem. So
Yep.
it takes a little more than just contact estimation.
Yeah, fair enough.
Yeah, Maani, you're using the learning bit to, fix the perception, recognize the contact point and feed that into a more estimation theoretic kind of framework, rather than, going for end-to-end learning.
Mm-hmm.
You try to do everything with learning. What's the current view or your view on this stuff? I like this separation where learning provides the support rather than be the main engine.
So my idea here, or my understanding here, is that this should be separated for the reasons that end-to-end at this point does not understand the structure of the problem, the geometry of this problem. I know people work on geometric deep learning, but none of them can solve the problem like invariant EK for that particular well-defined, nice setup. Basically, none of them can solve it as good as invariant EK. So it makes sense for the part of the problem that we can solve the problem correctly, we use geometry, and the part that is messy, we use data. Now, data is the learning part provides memory. So as you know, this common filtering or all the Markov processes assumptions that we make makes the robot memory less, and that's the problem. The robot has no notion of where I've been before, what happened, how can I learn and get better. This learning module to provide hard to estimate quantities. Contact is very difficult to estimate. Friction is even harder. Understanding what we're touching or what we're walking on is very difficult. The memory can help with that. This neural network can help with that part. But we don't want to lose the theoretical side that we can exploit the geometry.
Yeah, I agree with that. I like that. But memory, you mean by memory of the past, not immediate past while you're operating. This is the history. It's a
history, offline memory. I think we have problem with online memory yet. We cannot do online learning. I mean, kernel methods can do adaptations, but mixing them with neural network is a challenge itself.
Yeah.
As well.
Okay. Yeah, that's good.
You have some short memory here, right? So this is a window that you have at the bottom in the data, right?
Right. That's a very good point. So a lot I'm not showing, and you're guessing all of them right. So the data is over, let's say, 150 time steps. Okay. So the network looks at the window of time, which is something between gate cycle of the robot, whatever gate speed is moving, and then look at that and then say if it's a contact or not.
Okay, so this is what you meant by the future thing in the early part of it, that you use the window including the future as well, but in this it's just the past. Yeah, it's
the past up to now, but during data label generation offline, we need to look at the data after that to see if it's correct. Otherwise, we get outliers. So what happens, the false positives are killers for the filter. False positives means the leg is in the air. The network says that the foot is attached to the ground. And that's a problem because that causes inconsistency in integrating IMU. False negatives are not so bad for the estimation, but they are basically detrimental for the controller, because false negatives are when the robot leg, as soon as it touches the ground, the network does not know and we cannot estimate, because the controller needs to adjust the torque immediately or the robot might lose the balance. So this duality is also interesting here.
I'm curious about the transition points also, because I've seen in your video, for instance, going from this kind of pebbly type of area directly into a concrete slab, where very likely you will have two legs in one side and the other two in the other, or more. Yeah.
The performance has been fairly robust across terrains. We don't have any significant differences that we say that in this particular ground it doesn't work well.
Yeah, I'm just wondering for your contact prediction, as you do with your CNN, you would actually have the classification telling you which terrain you're on, and I can see that there will be transition places where, well, you have to take a call, but it will be both terrains, pretty much half the robot in one, half the robot in the other one.
Yeah, probably we get lower performance at those places, as you said, but our evaluations are, you know, middle pebbles, concrete. So the tables that we have in the paper are separating them. But I suspect you're right, and then at the transition, the performance might not be as good. But because it's just the moment, it doesn't affect the filter that bad. It doesn't happen.
Yeah, more for that's right. Yeah, more for the table, for the performance that you can actually put out. It might influence that. I know that you split. I mean, for testing, you differentiate that, but obviously you learned something in the middle. So the influence of that.
So Maani, do you have any more slides to show you, or just?
Yeah, I do. I just thought it's not fun not to have time to talk. How much more time I have, student?
Yeah, maybe another 5 minutes.
So I just touched on this equivariant models. This is more on the vision side. So it's along that idea of Lie groups. So Lie groups has become a center of my basically work, and I grew a love for them. They're very beautiful mathematically, and they usually makes everything better in robotics. So I have no regret whenever I use them. I got better results. So equivariant models basically are models that preserve symmetry. Symmetry, for example, 2D convolutions are translation equivariant. Or if you want to have rotation equivariant, means that if you learn features from an image or point cloud, when we rotate it, we want the features to have the same rotation, not that to be completely different and indistinguishable. This idea is applicable to perception, planning, and control. And potentially, this is the idea that will lead to learning dynamical systems, because equation of motions of robot from literature on non-holonomic mechanics and control, they are equivariant in some sense, at least in the theoretical level. This idea is also applicable with both kernels and deep learning, depending on how you approach the problem. So this is the kernel, basically method version of that. We want to solve visual odometry problem. We want to combine semantics and geometry. Challenges are we're dealing with textureless scene, partial overlap, noisy observations, dynamic objects, different densities. And that makes point cloud registration or RGBD visual odometry very challenging. So how can we approach this problem differently and in a unifying way? So one idea is that let's define an information space, a label space that can combine, let's say, intensity, color, semantic labels, and potentially other informations that we might get from neural networks or directly from sensors. These are typically labels that are independent of translation or rotation. For example, the semantic labels are view invariant, or color is somewhat view invariant, although it's affected by illumination. So we can combine these features using tensor product, which is essentially combine every feature from this vector with all the features for the other vector. What this gives us is that unless both features are consistent for a point, they are not a match. So there's an implicit data association happening when we combine it into a model. So this is how we create a hierarchy of information. Now, the key message here is that instead of matching point with point, let's think about each point cloud as a surface, as a function. If it's a function, we're not matching points. In some sense, we want to basically minimize the angle between two functions, or a better way to look at it is that we want to maximize the cross correlation between these two functions. So the whole point cloud will give me a signal made like this f of x here. So it's a weighted sum of labels for each point times a kernel. This is a Gaussian kernel. So this will give me a kernel density estimation of my function, and then I will maximize the cross correlation to get the transformation. This will allow me to use color and semantic labels at the same time during estimation. This, in a sense, generalizes the ICP. We can reduce it to weighted least squares as well. So if we're not doing anything fancy, if we just do frame-to-frame tracking, it works really nicely on some data sets on highway. A nice feature of it is that if you move very fast, it can still work well, because this kernel is not point-to-point matching. It will interpolate the neighborhood of every other point that is getting basically combined with to calculate the cross correlation. So this is a video of Kitty data set. This is just the stereo camera moving, and we are just doing frame-to-frame tracking and accumulation. So there is no SLAM or sliding window optimization. Now, this is a little more expensive, but we have a GPU implementation of it that can run at about 5 Hertz or 10 Hertz with some downsampling. So some acknowledgement for people who actually did the work. And I got to talk about the results. So this is the end of the talk. Thanks for inviting me again.
Yes, thank you very much, Maani. Let's ask any further questions if anyone has.
Hi, Maani. You went over very quickly on the last one, but I'm just curious whether you've seen some. I mean, this is the Kitty. I noticed this is a countryside. Whether you've seen similar results from some of the other data sets, more city oriented, for instance, on the Kitty, for instance, which I use. Do you have a similar visual odometry output?
On other sequences also, it works well. If there is a dynamic object and it comes very close to the camera, it can ruin the performance a lot.
Yeah, because it's frame to frame, right? What we're talking about is just frame to frame.
Yeah, it's not robust to that. We are extending it to SLAM, but it's challenging. We don't want to break the framework. We want to keep it like the not switching back to the previous backend. So one problem with the existing backend is that they don't use semantic information. They only use geometry. We want to make a backend that also uses these labels.
Good. And one final question also from the previous work, when you actually had the visual like orb SLAM and you have your estimators, have you played with mixing both results, basically fusing the results at all, basically, to see whether?
Yeah, that's exactly where we're going. So now one idea that basically comes to mind is that if this odometry is so good, why not build a factor graph on the robot, right? And then make SLAM. So I have some students working on it to make a real-time SLAM systems that combines vision with that odometry. I can give you an update when we have results.
Yeah, it sounds makes sense. Yeah, definitely. That's also Maani. I mean, very interesting, and I'm very, very, very happy to see where you guys are going with this. Very exciting stuff. Very, very good. Congrats.
Maani, I have a non-technical question. You got your PhD in 2017, and within about 4 years, you you get this kind of academic position and build up your team. Are you able to share some strategies or some suggestions to people like postdocs or senior PhD who want to go along this path?
Yeah, I'm going to stop my screen so I can see everybody.
Yeah.
So I think what I learned leaving CAS, Australia is far, so I had no idea what's going on in America. And America is obviously big and there are a lot of good universities. It's not, the environment is important, but what people do individually themselves probably is a big part of the work itself. Even here, ultimately students working in the lab and they have to do something. So that part of it is similar. But I think a good postdoc helped me a lot because I was very lucky to match with a group that somehow increased my performance exponentially. I could collaborate with some students and we had complementary skills. I wasn't just getting better at what I knew already. I was solving some problems. They had these legged robots and controlling it, and I was helping to add perception to it. So the outcome was much bigger than what I could do by myself.
So
but
you were a postdoc at Michigan, right? Initially,
yeah.
you were a postdoc and then become an academic, right?
And the postdoc was enabled because Mitesh, Jaime's previous student, was in California. Then Jaime basically sent me for internship to Palo Alto. That helped me to contact some people and come and visit and talk with Ryan and get the postdoc. So it was a sequence of events, not just moving around is good. Do an internship, visit people.
Yeah, I was gonna say, if I may interject, because I think that one thing that Maani is actually being very humble about in his own performance is that he was very keen from the very beginning to really make this happen exactly this way. I mean, he had a very hard time getting his visas because I was part of all this stuff. It was extremely, so this interest is what I think should be really highlighted. Shudon, you're asking about how you think that could come about. Well, not by sitting and waiting. That's kind of the message that I'm trying to say. I mean, he was very persistent, very keen on what he had in mind and where he wanted to go. I was extremely happy to support that because it was very, very, very much his own initiative. And I think that's something that people need to see. He made a comment, is look for complementary skills. That to me is essential. I'm sending right now another student to somewhere else that is completely new for the student who hopefully gets a visa. And it is all about being able to go there to challenge yourself and make sure that you bring your skills, but you actually learn from the other ones. Otherwise, as Maani said, you know what you're doing. You already have been doing that for a long time, but you don't actually learn beyond that. You can get a TRO 3 years down the track on that very specific field, but that's how far you will be able to go. So I think complementing is extremely important. That's just wanted to add that because I think it's critical.
Yeah, that's. I mean, working hard is essential, as Jaime said. And you shouldn't give up. There's a lot of. I remember I was complaining to Jaime that I have to go fill these forms and do that. I was saying, "Oh, this is life. You have to do it."
Yeah, and you have a particular hard life because going to the States for being an Iranian, this is
a lot of paperwork.
How hard can it get?
So Honda, I went to Japan for internship. It was still one of the best memories I have. I was very stressed that I'm going there to work in sound processing. I have no idea how to work with a microphone. I never learned. Still, I don't know. Jaime wanted me to do something. I never learned how to work in microphone.
You got a publication out of it and you use Japan, right? Can't complain.
But I think I just diving in and don't worry, you'll figure it out. And people usually, if they see you try, they'll help you. Eventually you'll come across people who want to help you if they see you try.
Try and perform, right? I mean, not just
perform,
try
right.
and perform. You have to. You had good presentation letters, so to speak, about the work that you're doing. Otherwise, Ryan wouldn't be welcoming you at all.
So good results, not giving up. good presentation is very important. In America is the focus on presentation is 100 times more than Australia. I think Australia was more relaxed in some sense. In America, it's like everybody needs to be a celebrity. If you're not a celebrity, you're going to miss out. So you really want to practice when you present and you talk. That's very important. So I encourage my fellows at CAS. We never worked together, but practice. When I was a student, I always thought I'm wasting my time if I'm practicing a presentation. I was always giving a terrible presentation. But spend 20%, 30% of your time instead of working, just be able to talk about what you do. That will give you much more reward than doing twice of that work and not being able to explain what you do. That's very important.
That's a good message, Mark.
Yeah, I agree, actually.
That's a very good message. You've done very well. Well done.
Okay,
Yeah, I think one thing we're losing out here is because of the situation right now. All this exchange of students that were coming back and forth and stuff like that is kind of being lost on us. That's very hard to do now.
I imagine it's difficult to hire international students now in Australia.
Yeah, it's impossible actually, and to send people out and all the visa issues. Anyway, that's making this the experience that you went through, for instance, and myself and most of my students. It's really lost at the moment. It's very hard to do.
Yeah, Liang, I think you have a question, right?
Hi.
Hi, Liang.
Can you see me?
Can't see you.
Your video is not on, but
Have a, yeah.
Okay, we can hear you now. Yeah.
Happy New Year to everyone. Hello, Xiaodong. Congratulations to your new position as a professor. Yeah. And thanks, Maani, for your wonderful talk. I just have a very quick technical question about your application of invariant state estimation algorithm in the beginning of the talk. So you use IMU to provide odometry for the robot state, and you also use the context sensor as some sort of landmark, which is measurement that provides the measurement update. Now, and with all those beautiful equations provided, I'm just wondering if I were to have wheeled robots, 4 legs, instead of 4 context sensors, the wheels have encoders. This should work equally well, right, for your algorithm?
That's a good question. We are right now extending this to a wheeled platform, and this occupied my mind for a while. What's the relationship between legs and wheel? So you can imagine wheel is a circle with infinite legs around it. That's wheel. So we don't have contact. So that goes back to what the discussion that Lisa raised, that we need some way to relax that zero velocity constraints, and that might be wheel velocity or acceleration.
Can I just use encoder from the wheels, which provide
so the problem with encoder is that to do correction, we need body velocity, right? Now, the body velocity that we read from wheel encoder by no means is the true body velocity. Why? Because if you lift the robot in the air and the robot goes with the maximum speed, your encoder is telling you you're moving as fast as you can. And that's completely wrong. So what we want is the ground reference body velocity.
Oh, okay. I guess my question refers to a robot which never lifts its leg above the ground. The wheels are always in contact with ground. And in that case, I think your algorithm should work perfectly still, right?
In an ideal case, yes, there are wheel slip and disengagement.
Yeah, I think it's slippage. The slippage is the key question.
Is the problem.
I mean, with the wheel thing, I think the non-holonomic constraint is the thing you need to look at, Maani.
Mm-hmm. I know you have a paper. I've seen that. You do pseudo corrections.
Yeah.
Right.
This is without any fancy KF. If you add your invariant stuff, it do a much better job. I mean, that was a direct filter, not even error space.
Yeah, we started looking into that. I think we need to go around some of his ideas, see what works in practice, because ultimately it should work on the robot. If it doesn't work,
That's right. Yeah.
that's not good enough.
Okay, I guess I can reserve some of my questions offline. Thanks very much for your
Yeah,
time.
definitely. Send me emails if you have more questions.
Thank you.
Sure, I think you're muted. Yeah.
Yeah, I think if there's no further question, we can conclude the talk today. Thank you very much, Maani, for giving us this talk and share your information about technical and also personal.
Thank you so much. It was great.
Yeah, we will keep in touch. We'll keep in touch.
Thanks, Maani.
Hopefully
Great
I
to
can
see
visit
you.
you.
Thank you.
Bye.
Cheers.
Cheers. Bye.